Alright guys, welcome back. This lecture is going to be on ionic equations. So what we're really going to deal with in this lecture is looking at when you have or are handed a beginning of a reaction, how to predict the products, the states of the products, and then we're going to talk about the molecular equation, the complete ionic equation, and the net ionic equation. And those are the three equations that are typically asked for by teachers when you're in class. So let's begin. We're going to start our discussion on ionic equations. So first, let's discuss what each of these actually is. The molecular, the net ionic, and the complete ionic. All right? Molecular equations are chemical equations that show the complete neutral formulas for every compound in a reaction. So when your instructor asks you for a molecular equation, they're asking you for the equation as it would appear if everything was neutral, if all the ionic bonds were in place. So you shouldn't have any ions, any charges like plus or minuses floating around. Everything should be in a neutral form, and you can also go ahead and put the state with it in case it's aqueous or solid. Sometimes you might have a liquid or a gas. So if you move down, the next step is the complete ionic equation. And the complete ionic equation is a chemical equation that shows all the species as they actually are present in solution. And then in parentheses it says ions. So what does that mean? Well, when we have substances, specifically ionic substances, that are present in an aqueous solution, and they're in an aqueous state, which we find with the representation AQ in parentheses, that means that these ions will actually break apart, or the ionic compound will break apart to formulate ions in solution. So when they form ions in solution, now we're starting to talk about actually having the individual ions with their charges as they appear in solution. So what's the net ionic equation? It's an equation showing only the species that would actually change during a reaction. So just because these all break apart into ions, sometimes we find ions on the left and the right side in equal amounts, and they appear as ions in the reactants as well as in the products. And we call those spectator ions because they're not participating in any type of a reaction. They're aqueous and broken apart as a reactant, and they're found in the exact same state as the products. So that means they did not participate, nor were they involved in the reaction. They were spectators, and therefore they get crossed out, and they are not placed in the net ionic equation. So as always, the best way is to start getting some practice. So let's start with this equation here, and I'm going to walk you through this step by step, and then we'll do one more from the start. All right? So technically, the states are given to you here, but your instructor doesn't have to give you the states. You should be able to look at and find the states for yourself. But as you can see, you have the aqueous here, the aqueous here. Now when you have aqueous, that means that these will break apart and they will form the proper ions in solution. So the first thing we want to do before we start making ions, we need to complete our reaction here. So in order to complete this, we know that all these would break apart and they could potentially reassemble with the respective cations and anions. So if I look here, I'm going to have K from potassium. K plus will be available. I'll have I minus available. Now this is not balanced. I'm just giving you what's available. I have Pb. Hopefully you should be able to follow that the charge on Pb here is going to be 2. Because I have a 2 present here, I need 2 of the nitrates. Nitrates, which is one of the polyatomics you should be familiar with, nitrate has a minus charge. And so lead has a 2 plus charge in order to give us what we see here. Now, if I were to work this out, and we'll talk about balancing it in a minute, but if I were to work this out, what I would end up doing is saying, alright, so the potassium and the iodine dissociate from one another, and I'm going to bring the potassium and the nitrate together. So one of the things that I'll have is KNO3, and that's how I would write it, because a plus and a minus charge would cancel each other out. So I need one potassium and I need one nitrate. Remember, the nitrate comes bundled together. It's NO3. We do not break apart those oxygens and nitrogens. And then the other portion we would have is the lead as the cation and the iodine as the anion. And so this could form lead iodide, and lead iodide would be PbI2. Now, that comes from the fact that there's a 2 plus charge here, a minus charge here, so I need 2 iodines at -1 each to neutralize my 2 plus. So if I had this equation here, and then I would have to go through and balance it, that would be the molecular equation. Now, there's a couple things I'd want to include. I would want to include the states. Now, when you're looking at the states, there's a table that we use in classes, all right? And that table is something that you should be able to find in any textbook, or you could look it up online. And it tells you the solubility rules. So it so happens that nitrate is always aqueous. It will always break apart. However, the iodine has a couple exceptions, and one of them is lead. So this will actually form a solid state. Now I'm going to write this over neater on the next page. All right. If we look at this, we still need to balance it. There's 2 potassiums here on the reactant side, so I'm going to need a 2 in front of my potassiums over here. The iodine, there's 2 iodine here on the left, there's 2 on the right for the PbI2. The lead, there's 1 over on the reactant side, there's 1 on the product side. And the nitrate, NO3, there's 2 of them on the reactant side, and now there's 2 on the product side from that 2 that I placed in front of the potassium earlier. So we're balanced. So let's move to the balanced equation. Now I've reassembled it here. You have the lead in front and then the potassium nitrate coming second. But this is still the same reaction. So this balanced reaction right here with all of the states would be considered your molecular equation. So the next thing we want to do, and I'll abbreviate this a lot, is the complete ionic equation. So that's the next step in line. And this one is probably the most tedious, all right? But the reward is, once you get through it, the net ionic equation is relatively simple. So let's look at the complete ionic equation. If I were to break this apart, all of the aqueous states are going to remain in their ion form in the complete ionic. However, if I look here, the PbI2 is solid. And when it's solid, that's telling you it's going to form a precipitate and come out a solution. Solids do not break apart back into their aqueous states. They're going to come out as a precipitate. So we keep this as a complete solid in the complete ionic equation. So let's break this down, and remember you have to keep your stoichiometric coefficients. So we'll start with potassium on the reactant side and move all the way across. I have 2 potassiums with a plus, state aqueous. Next, I go to the iodine. I've got 2 I minus aqueous. All of the aqueous up here, like the potassium iodide, break down into aqueous in the complete ionic. That's what it means to be aqueous. You break apart into your ionics pieces. Okay. The next, this is aqueous, so the lead, we only have 1 of the leads. It has a charge of 2 plus, I'm going to have 2 of the NO3s. Now some people say, oh, isn't it 6? No, there's 6 oxygens. There's 6 oxygens here. But remember, the NO3 comes as a group, so that 2 that's enclosing the parentheses, or the nitrates enclosed in the parentheses, the 2 being distributed to it is telling us we have 2 of those nitrate groups. And both of these are aqueous. The lead is aqueous, and the nitrate is aqueous. Now, these are going to give, so I'm continuing my reaction down here. This whole thing will be the complete ionic reaction. This is going to go over to our products. Now, we said the solid will remain a solid because it's not aqueous. This will be our precipitate. All right, so you're going to have your solid. Then you're going to have 2 potassiums, aqueous. This is coming from the potassium nitrate up here. I've got 2 potassiums that are aqueous, plus I'm going to have 2 nitrates that are aqueous as well. This is from the potassium nitrate. Now, what you'll do, this is your complete ionic equation. You're going to go through and you're going to look for your spectator ions. In this case, I see 2 potassiums one on the left and one on the right, so they're gone. And then I also see that the nitrates, there's 2 on the left and 2 on the right, so they're gone. So what I want to do for my net ionic equation is take any ionic pieces that come together and form a precipitate. So what I just circled there is going to be the essence of our net ionic equation, and we'll do that on the next page. So if we're going for the net ionic equation, we're going to have 1 lead, 2 iodine, and then we're going to have a lead iodide. All right, so let's do that. So this is for the net ionic equation. And I might go back and forth a little here just so you remember. So we said, go back here and look. We have 1 lead ion, Pb2+. It's in an aqueous state, it's a reactant. Plus, if we go back, we have 2 I- that are aqueous. So we have 2 of our I-, it's aqueous. And then that is going to yield, I wrote a little big here, so we're going to go to the next line, the lead iodide right here as a solid. So that's going to yield Pbi2 as a solid. And there you go. That would be your net ionic equation. So the complete ionic, you can see, takes a lot more work. It's a lot busier there compared to the net ionic equation. And the net ionic equation is the final payoff. It's the actual reaction that's happening when we take out all the extra busyness from the spectator ions. All right? Now I just want to point out here, if both of your products are aqueous and you don't have a solid precipitate, you would have no reaction. Because if you have all ions on the left and an equal amount of all ions on the right for your product, that means they're all spectators, they all cancel out, and there's no reaction overall. So keep in mind, while a lot of these problems are set up to give a precipitate so you can practice your complete ionic and your net ionic equations, if you went through and you found a complete ionic equation where all the ions were spectators and nothing was left, then that means that you have no reaction for your net ionic equation. There was no reaction that occurred. So let's do one more here. And we're going to start out very basic, and we're going to work all the way through it. So let's take silver nitrate, AgNO3, and that happens to be aqueous, and we'll combine it with sodium bromide. Sodium bromide is also aqueous, and you could determine that from your charts. So if I wanted to figure out what else this comes into, hopefully you saw from before, we're going to break this apart. Ag and NO3. We know NO3 has a minus charge, so therefore if it's a 1-to-1 here, the Ag must have a plus charge. So I'm going to be dealing with, I'm going to put this down here, Ag plus, I'm going to have a NO3 minus, I'm going to have a sodium plus, this is coming from the sodium bromide, and I'm going to have a Br minus. Those are the 4 things I have. Now, the silver and the nitrate have already been associated together. They're going to dissociate, and the silver is going to come together with the bromide. So I'm going to get AgBr. And if you complete this and you look at AgBr on your solubility table, you'll find that it's solid. And I did that on purpose because we want to practice another complete net ionic equation. We don't want a no reaction here. The other one that we're going to have is the sodium and the nitrate come together to form sodium nitrate. Now, I also picked this one out because it's relatively simple in the fact that all of these have a plus and a minus charge, so therefore this is already going to be balanced. If you look, there's 1 silver on both sides, there's 1 nitrate on both sides, there's 1 sodium on both sides, and there's 1 bromine on both sides. So you should be comfortable balancing. That is something that's learned in earlier chapters. You will need the ability to balance molecular equations, but for the sake of time and learning, we're going to use this already balanced equation here. All right? So let's go ahead and move over, and we're going to start our complete ionic. So for the complete ionic, if we look back here, we've got aqueous AgNO3, and aqueous sodium bromide. So each of these is going to break apart into those respective ions. So let's start with that. That means we're going to have Ag plus aqueous. And then the next thing we're going to have, if we look at what the Ag was attached to on the left side, it's the nitrate. So we're then going to have NO3 minus aqueous. And then if we look at what else we had, let's go back, we have sodium bromide. So we're going to get sodium plus and bromide minus, or bromine minus. Sodium plus, this is aqueous, plus the bromine minus, which is aqueous. Sorry, I'm getting close to the side of the screen there. Alright, so once we have that, this is going to lead over to the other side. So, what do we have on the other side? We have AgBr as a solid, so silver bromide is going to form a precipitate. So let's get that in there. And then we're going to have sodium nitrate, and this ends up being aqueous. Sorry, we didn't put that in earlier. If you go onto your chart, all of the nitrates are aqueous. There's no exceptions to that rule. So we'll get a sodium and we'll get a nitrate, both of which will be aqueous. Plus and minus charges, respectively. So if I go through and I'm looking, the NO3 minus, the nitrates, are going to cancel as spectators, and the sodiums are going to cancel as spectators, which leaves me Ag plus, Br minus, and AgBr. So this up here was my complete ionic equation. This is the complete ionic equation. If I do the net ionic equation, I'm going to take Ag plus, that'll be aqueous. I'm going to add it to the Br minus, also aqueous. And that is going to give me AgBr, and that's my precipitate, so that's solid. There is my net ionic equation. My net ionic equation is Ag plus aqueous plus Br minus aqueous going to AgBr solid. Alright? So I hope that this helps to clarify the molecular equations, the complete ionic equations, and the net ionic equations. So keep in mind a couple of things that you should be able to do after this point. You should be able to be given, to start with, a set of reactants, and you should be able to predict their products and complete the reaction. Then you should be able to assign states, aqueous, solid, liquid, or gas, to each of those products and reactants based on the solubility table. Once you have that complete molecular equation, which is the reactants and products with their proper states, that's what a molecular equation is, you're then going to balance it. You should be up to date with your balancing skills. If not, you should go back and you should watch a video on balancing. You then are going to do your complete ionic equation, breaking down every ion present in solution. The solids stay by themselves as precipitates. Cross out your spectators, and you should be able to give a net ionic equation. That's the final goal. Get to the net ionic where you show just the ions that are forming the precipitate. Alright, so I hope that this lecture helped you guys. Continue to study. I will be posting other lectures up soon. Thank you very much for watching. Thumbs up and comment if you like the video so that I know what was helpful. And please remember to subscribe because it's the quickest way you're going to find updates coming out for these videos.